Hello everyone. I can't believe I become a YouTuber. And tonight I didn't mean to ruin your fall break, but I have to do two things. One is helping with the homework 7, so you all see the problem set. The other thing is go through the understanding of concept questions in our textbook chapter 7. So as you know, this is quite a senior level undergrad course. So especially in this homework, you'll find we are putting things together, what we learned before. So question one. Question one is quite an understanding concept problem. It's asking comparing the boundary layer thickness and heat transfer, convection heat transfer performance. So from ME309, the fluid mechanics, whenever we see a fluid problem, we first check the Reynolds number. And in this case, it's a flat plate. So we use the Reynolds number. So what is the characteristic length here? The distance from the leading edge, right? And then we check it for 5 millimeter and 40 millimeter. We find, okay, they are both smaller than 5 10 to the 4th. So they are both laminar flow. That's good. And then to calculate velocity boundary layer, according to the textbook equation, we know, okay, it's 5 times x over the Reynolds number. Let me note it here. Reynolds number. And then also we know the thermal boundary layer is just this boundary layer times the total number, 1/3, right? That's it. And then the problem asks us to comment how heat transfer would compare for small and large objects. So basically the idea is, although we are not always dealing with a flat plate, but the flow is still governed by this form of Reynolds number. So things doesn't have to be flat like this. But for some, we call that streamline-shaped objects. For example, a blade, an airfoil in the turbine. When we are analyzing how it heats up by the combustion flame, we can also develop a boundary layer, and there may be a turbulent transition somewhere. So we can still use this kind of method to think. And again, locally, the heat transfer coefficient will first decrease as the laminar boundary layer develops, and then it will jump as the transition region, and then again decrease as the turbulent boundary layer gets thicker. Sorry. And this is one thing. The other thing is, of course, we have some blunt body, for example, a cylinder or sphere. So besides this transition zone, it's also possible to have a boundary layer separation, right? So the boundary layer doesn't have to follow this shape. So here it can separate, and here become a high pressure zone, and there's not enough mixing, and we have a effectively super thick boundary layer. So the heat transfer here will be very bad, right? And I think if you can comment this part, it's good enough for us to give you full credit. This one, of course, if you know that's even better, but this is the full picture. And now problem 2. Problem 2 is saying, okay, what if I'm interested in only one small segment of this plate? So before we go to this part, let's see, how does the heat transfer coefficient change with respect to the distance from the leading edge? we can have the local heat transfer coefficient. There's also a definition called the average heat transfer coefficient, but it can also be a function of the distance from the leading edge, right? So I think we talked about this last time. So which one stands on top of the other? For laminar. So for laminar, this is the critical Reynolds number position. So the average stands on top of the local coefficient because it's keep decreasing and it's an average, right? So at this point, it's basically averaging from here to here, right? So to evaluate a small segment, let's say if this two x1 and x2 are here and here, we have three different ideas we offer, right? One is to find the coefficient of the average location, right? We do this. By doing this, we are evaluating this point. Okay? This is one thing. Calculate this one and plug this number into the local convection coefficient. The second idea is saying, okay, let's try the average of the local convection coefficients. So the convection coefficient, local convection coefficient of x1 is here, the other one is here. Then we are looking at the average of these two values. So if I zoom in, one is saying, okay, I want to use this number as the average of this segment. The second idea is saying, okay, I want the average of these two numbers, which could be here. Is that clear? Third idea is saying, okay, can you use the average coefficients of 0 to x1 and 0 to x2? How to do that? Right? So the idea is, so by definition, this h bar is that you take the integral from 0 to the x you want to evaluate of the local convection coefficient. I use x prime. Divide by this distance, right? X minus 0. This is the definition. So now what you are actually want to calculate is integrate from x1 to x2. Then divide by the length of this distance, x2 minus x1. Then obviously this one should equal to 0 to x2 minus from 0 to x1, right? And then you can, by definition, plug this thing in and then find a function of this guy. We can call it h1 to 2, h bar 1 to 2 equals to this guy with respect to the definition of this thing and x1 and x2. So we notice, okay, the third idea is actually by definition the average convection coefficient is the exact solution of this average convection coefficient between the segments. So it can be used everywhere. However, for the first and second method, it's just an approximation. So it only works if the convection coefficient function, the curve of this function, looks smooth. So basically, these 2 points have to be close enough and in the same zone, either both in laminar or both in turbulent. Okay. And the second part is just to plug in the numbers. But one thing we forgot to mention is since we didn't specify what temperature we are discussing, so let's just use the room temperature to evaluate all the thermal properties. Okay, I realize you didn't have a chance to ask a question, but let's see, you can shoot me email. Or leave notes at the comment. Well, I prefer emails. So third one is a mass transfer problem. So we tell you, okay, here's a pool filled with water. We have wind blowing here. And we say, okay, the temperature are both 30 degrees C, right? The infinity is this much, and the water is also at 30. So there's no heat transfer, uniform temperature. But there is mass transfer. So we measured the mass transfer rate. Oh, let me use the black one again. We measure the mass transfer rate, the Q of mass. This one we know. And from the book we know, okay, the mass transfer coefficient, the area. Do we know the area? We know it's 75, right? And what is here? Is if this one is kilogram per time second, we give you hour, but you can convert it yourself. So here should be the density difference, right? So this one should be in kilogram per meter cube. Or the book sometimes prefer in concentration. So here we use mole per second, and here we use mole per meter cube. So this thing differs by a molar mass, right? Since we're only talking about one component, one chemical, which is water in this case. Then how to evaluate these two cases? Then we're using some knowledge in Thermal 1 ME200. So for the first one, it's an assumption. So basically at a very close neighborhood of the water surface, we assume there's a phase equilibrium. So basically at root, oh, by the way, there's one hidden condition we didn't give you, but you should definitely know is the pressure is at atmosphere pressure, right? So we're given the pressure, given the temperature, then the thermal state is determined, right? Two parameters we already know. And locally, it must at equilibrium. This is from ME200. So we can calculate the vapor pressure at the surface of the water, right? Or go to the charts to get that. And another condition we gave you is in the wind, the relative humidity is 55%. What does this one mean? Right? So if the wind is really humid, it has the same amount, same density of water vapor, then there will not be any mass transfer either. The 55, this is to say, okay, the concentration or the density of the water vapor is only 50% of the saturation case. So at the same temperature, at the same pressure, we can calculate the saturation. Either you can call that in terms of the density or concentration, or sometimes we use the saturation vapor pressure. Right? These are all coming from the equation that PV equals to nRT, or P here. Sometimes we put an M here, right? We can write P equals to, we write rho RGT, right? RGT or R bar T sometimes. Depends on which language you are using, right? All comes from this equation. because the water vapor is only a small percentage. It's not liquid, so we can think it as ideal gas. Okay, then we know, okay, at the surface, we use the saturation water vapor density. And this one is just 55% of that. And now we can evaluate this one. Now the last question. Last problem. We have dealt with this kind of problem before, but at that time we directly gave you what's the convection coefficient. But this time we give you the conditions, the velocity, the temperature, all this stuff. We want you to use the empirical relations, right? Empirical relations. And by the way, there are 2 or 3 empirical relations available for fluid flow across a cylinder, and they are kind of close, and whichever you use should be fine. So we start with the Reynolds number, and we also know the Prandtl number. And in this one, we know one correlation. For example, you want to use the, I don't know, you want to use the CD or, what's the other called? Hilbert, right? Whichever you want to use, you can get the Nusselt's number. This is the average Nusselt's number. And then from this one, we can get the heat transfer coefficient, right? And then after this one, we come back to the thermal resistor analysis, right? So first we say, okay. So inside the pipe is water vapor, keep at a certain temperature. We call it. And we add an insulation layer with thermal conductivity of R1, R2, and then here is just this convection. Right? This convection is here. So the first one, there are 2 thermal resistors, and this one is obviously like 1/H because it's a cylindrical system. We calculate the R prime per the resistor per unit length, right? The length of the cylinder is normalized. So pi d, but remember this d now is this diameter itself plus twice of the thickness, right? And then this one, the equation. Right? R2 is this one, R1 is this one. Right? Okay, and then you can repeat the calculation, but remember this H, there's a thickness hidden here. Okay? So every time you need to recalculate the Reynolds number, use the correct correlation. And since we gave you a reasonable range of the thickness, so actually don't need to change the correlation. You can just use MATLAB to code it for once. And recalculate Reynolds number, recalculate Nusselt H, and put the H here. And that's about this question. Okay. In this part, besides all the homework problems, there's one kind of I always ask you to look for if there's a generic problem or a routine calculation, means one type of problem that can have many derivatives, and you only need to remember this standard procedure, and you can solve all kinds of derivative problem, right? So one thing I would like to mention, maybe this is the hardest, the complete version of this generic problem is, for example, you have a wet sphere or cylinder. Wet means have water, right? So it can involve mass transfer. A wet cylinder possessed in a hot air. So this T infinity can be high. And then it has a certain humidity, but definitely it's smaller than 1. So the hot air blowing through this ball is heating up this object. But on the other hand, because the humidity is the wind is not saturated. It's not saturated with water. It can take away some water by evaporation and remove a certain amount of heat. So basically, I can tell you all this thing and ask you to calculate the temperature of the sphere by the energy balance. Does it make sense? So one thing that connects the heat and mass transfer is that, so in the Nusselt's number, and the Nusselt's number of mass transfer, what do we call this one? I forgot. Schmidt or Standard? Oh, Schmidt number, right? Schmidt number, I found it. Okay. Schmidt number. By the viscosity divided by the binary diffusion coefficient, binary diffusivity. So the key is these two things share the same Reynolds number because it's the same geometry, same velocity, and just that fluid. Okay, we just mentioned that these two cases, although it's two different correlations, but it looks to be a two different correlation, but they share the same Reynolds number. So the only difference is to replace the correlation, the Prandtl number with the Schmidt number, and you will get the mass transfer Nusselt's number. Then calculate these two numbers separately. So each of them can be a separate problem, but now we combine them together. How? So firstly, as we know, we can write down the mass transfer coefficients, Q equals to HA, the temperature difference. I write T infinity first, because I mentioned it's hot air, right? And the other thing is the mass transfer coefficients. So actually this rho surface minus rho infinity can be written as the rho saturation, which these two equals each other, times 1 minus the relative humidity, which relative humidity is the saturation density, saturation vapor density, the rho infinity is the saturation density times the relative humidity, right? And then we notice, okay, the unit of this term is kilogram per second. And there's a phase change, so we use the latent heat, basically the enthalpy between liquid and gas phase, which is in the unit of joule per kilogram. And put this together, this will give you a watt, and that forms the energy balance between these two heat and mass transfer equations. And I think this is the combination of the heat and mass transfer. That's the generic question. And so, yeah, as I mentioned, by solving this one, you will get the surface temperature. And of course, you may need to do an iteration procedure in the real case, but if we give this problem, I think we'll give you some hint. Because after getting this one, you can evaluate the thermal properties. Okay, let's take a look at the understanding concept problems. So first one, what is? Since not if you read the book of chapter 7, you find okay, because we only do 1 week's lecture, so we only cover half of the total context. So again, I will only talk about the one the understanding concept question related to what we covered. So what is external? What is external flow? It's the main difference is the boundary layer development is not limited by the surface on the other side, right? In contrast to the internal flow, which we have we can define a fully developed flow, right? So external flow, the boundary layer keep developing, keep getting thicker. And what is an empirical heat and mass transfer coefficient? So basically, only for the laminar case we have the exact solution, but in other case, combined case, for other shapes, especially with the one thing is when you transit to turbulent, we don't know. The other is the separate boundary layer separation is another problem. So we just do a lot of experiments, and putting all the results together. In terms of this equation, actually, in terms of this thing, you by definition of this equation. And how does velocity boundary layer change varying distance from the leading stage? That's our problem one, right? That we want to test you in the problem one I just explained. And for turbulent flow, what happens? Sure, I also mentioned that, right? Relative velocity, thermal concentration boundary layer, thermal and concentration boundary layer are very similar, right? Only changes the material, this material property. It doesn't change where the transition happens. Yeah. And how does local convection heat mass transfer coefficient vary with distance? That's what I explained. Remember in problem 2, right? So the local one looks like this. There's a jump, but there's a jump at the transition zone. But the average from leading edge to that location is for laminar zone stand on the top of the local one, and here because it's an integral, it doesn't jump, but changes curvature. It's not smooth, right? And Nusselt's number looks like this. And actually, boundary layer also looks something like this, right? Next one, local heat transfer coefficient affected by the existence of unheated start lengths. So this part, unheated start length, we didn't cover, but basically it's saying the velocity boundary layer start developed from the leading edge, but thermal boundary layer didn't start develop. So it's thermal one start developing from a certain distance. So basically it's kind of so at the beginning of this one, the convection coefficient is still a quite high number because it just start to heat up. That's the idea. You can look at the equations in the book. If just in case you see that scenario when you start working. What is manifesting boundary layer separation from a cylinder, circular, a cylinder cross flow? How separation influence by upstream with laminar or turbulent? This one we also talk about. We also mentioned earlier. So after the separation, the heat transfer is terrible. Is greatly reduced. And remember the golf ball case, right? We studied in ME309 the fluid mechanics. So basically, by turning the boundary layer into turbulence earlier, the boundary layer have more momentum and it can follow the shape better. So delay the boundary layer separation. So how is a variation of local maximum minimum? So yeah, now we have basically kind of one or two, more than one possible transition zone, right? First question, where does it turn to turbulence? Second, when you turn to turbulence, the heat transfer actually enhanced locally. But when it separates, the heat transfer deteriorates. Tube bank we didn't cover, jet impingement we didn't cover, so, and also porous media we didn't cover either, right? Packed bed, fluidized packed bed is like a foam. Fluidized bed is like you have particle can move within the bed. We haven't covered this one. Film temperature use this all the time. So we think the boundary layer thickness is very thin. So we evaluate the thermal property with the average of the free stream temperature and the surface temperature. Bank to packed bed, we didn't mention either. Okay, that's it. So if you have more questions, shoot me email. And if you want to leave comments, I don't know if I will have time to check that. And feel free to like and subscribe. Thank you.